So hi everyone, today we are going to see a problem called largest contiguous sum subarray. So like you'll be given an array and the task is to simply return the subarray, a continuous part of the array which will produce the maximum sum for you. So like if you see here, this is the maximum, this is the subarray given to me, this is the array given to me, and now the maximum subarray here, like the sum of all the elements which would give me the maximum sum is these elements. See if you sum all the elements in this set basically, which is 4, minus 1 is 3, minus 2 is 1, 1 plus 1 is 2, followed by 5 is 6, sorry, 4 minus 3 is going to be 1, plus 1 is 2, plus 5 is 7. So you'll get a maximum, the answer for this problem is basically 7. So this is the subarray which will give us the maximum sum. So there are actually a couple of ways to solve this problem. We'll start from a very brute force to the most optimal approach to solve this. So the first approach that comes to my mind is the brute force approach, like just do what is being told to you. So what can we do in that case is just generate all possible pairs. This works perfectly fine. Use two for loops, generate all possible pairs of I comma j. You can do it using two for loops, and for each of the I comma j pair, calculate the sum. Okay, calculate the sum from I to j. Yeah, this is a very brute force solution. Why? Because generating all the pairs would take you an order of n squared time, because you are going to use two for loops, and calculating the sum for each and every pair I comma j is again going to take you n more time, because you have to go all the way from I to j and then calculate its sum, right? So this would bring you to a big O of n cube time complexity, which is a very bad solution. In fact, n cube is not at all accepted. There might exist some more optimal solutions to it, but let's see where we can optimize in it. Okay, so one place where I find we can optimize is this part, because I think we cannot avoid generating all possible pairs of I comma j. So one possible place of optimization is this part, wherein calculating I comma j, like how much this would ideally take n time. Given I comma j, you need to go all the way from I till j to calculate the sum of all the elements, right? This would take n time, but here I am planning to optimize it further. Like how can this be optimized? So I am, spoiler alert, I have done this problem. So this is going to be, you can optimize this to a constant time. How can this be done? So I am going to tell this now. So this is the first approach that we have. So let's keep this as it is. If we make this a constant time, if we make calculate I comma j to a constant time function, then we could bring it down to n square, which is still bad, but it's better than our previous approach, right? So what we would do here is maintain something called the prefix sum. So here I'll say my prefix sum is minus 2. Here I'll say my prefix sum is minus 5. Just add it. Here I'll say my prefix sum is minus 5 plus 4, which is minus 1. And here I'll say my prefix sum is minus 2. Here I'll say my prefix sum is minus 4. Here I'll say my prefix sum is minus 3. Here I'll say it is going to be 2. And here it is going to be minus 1. So you can maintain this kind of a prefix array, which will have all the prefix sums basically. So that is what this array does. Now if you are given two indices, let's say this I'll be given index 0 and 1 2 3 4, index 4. Now I am asked to find the sum from 0 to 4. So now rather than going all the way from minus 2, then minus 3, 4 and minus 1, all I can do is, I know that it is going to be minus 2 till this point, okay, and from that I am going to just subtract whatever was my previous, like minus 2, whatever was my previous, like not this index, my previous one, so this guy. So if I remove till this point, I will get all the values which are here, right? So this is 0 because there is nothing behind this. So then you get the sum to -2. Let me take another example. This is for 0 to 4. Okay, now let us take some more example, tricky example. Okay, 4 to, let's say, 4, 5, 6, 7, 4 to 7. So if I'm asked to calculate the sum between 4 to 7, then it is 7 is sum 7, it is 2, and then I'm asked I should remove 4 from it. So I should remove this part, all of this part. So that's summing to -1, right? So if I do this part, then I'll get 2 plus 3, which is 2 plus 1, which is going to be 3. So if you start from 4 and end at 7, then the subarray, sum of the subarray that lies between this part is equal to 3. And if you check it also, like this is going to be 5, 1, 6, this is -3, 6 minus 3 is going to be 3. So this is how you get it. And this is another solution. This is the other optimal solution when compared to the brute force one, and this would take n square time, because now all you have to do is just compute it, just generate all pairs of I comma j, and for every pair of I comma j you can calculate the sum between I to j in just constant time. And so this would give you an order of n squared time complexity, but also an order of n space complexity. Why? Because we are storing this something called this prefix array here, which is kind of a trade-off, right? You have to store this in order to achieve that optimal this thing. Now there is this algorithm. I would call, rather than calling this an algorithm, I would call this a cheat. Like, it's very hard to come up with this kind of an approach in an interview, but yeah, if someone is well aware of this algorithm beforehand, or someone is very intelligent to come up with this in an interview, then yeah, I am not that intelligent to come up. So I'll just explain this algorithm called Kadane's algorithm. So this algorithm, the best part about this algorithm is this takes order of n in time, which is far better than our n squared better approach, and also constant space. So it doesn't take any extra space. This is literally a brilliant solution. Okay, so we'll just deep dive into how this works. So Kadane's algorithm, what Kadane said is, just keep moving. Okay, you want to keep moving. So you have -2. So let's say, okay, I'll just reframe it. So let's say my maximum subarray sum so far is -infinity, right? This makes sense, right? Maximum subarray sum so far is -infinity, and now I find a -2. Well, that is perfect, but my -2 is better than my -infinity which I had, right? So I will update my maximum sum so far to -2. Got it? I'll update. So so that's what, right? Your -2 is better than -infinity, so you update it. Then you find -3. Okay, is your -3 better than -2? No, your -2 is far better, right? Or can you add both of them to get to a result? No, if you add it, it becomes -5, which is still worse. So here I am going to just keep my -2 as it is, which means at this point in time the maximum subarray sum is -2. Okay, this is fine. Now you get to a point called 4. So here I would ask a very simple question: what is the maximum subarray that I can make staying at this point? Well, it is 4. How can you say it is 4? Because these two guys have not contributed anything to my sum. Remember this, these two guys have not contributed anything to my sum. How will you know that someone is contributing to something or not? So this is made from the fact that if someone makes a contribution to me, then his adding of some number to him has to produce me a result which is at least greater than 0. Like, see, if here rather than -3, like that case would also come up. But let me just say, so this guy, like, we'll just go with the flow. Okay, we don't get confused. So here this guy is contributing nothing to my sum. So just the previous part, why is this guy not contributing anything? He doesn't have anything. Like, even if you account to take him into yours, you would get a sum of 1, which is still worse. So just don't count this guy. Now comes the the core of the algorithm. Now here I have a 4 now, and I can contribute a 4 to my next guys, right? So now I am asking, hey, -1. So can I contribute? I'll take 4 and -1, and I'll update my 3 here, and I'll update my sum to be 4, maximum sum so far. So if you observe, the above array is keeping track of whatever is the maximum sum that I have encountered so far. So here the maximum sum I have encountered so far is 4. But what is this second array doing? This is a very important understanding that you have to make from this thing. This array is storing the prefix sums, right? It is, whatever it is doing is, it is continuously adding every time. It finds the -2, it just adds, let's say it was 0 initially, okay? It finds a -2, then it adds -2 to this. But since since adding -2, we don't want this result to propagate further. Why? Because this result will further degrade our sum, right? Even if you get a maximum sum in future, it is going to degrade your sum. So we just tell you, I can't help you with your sum, all I can give you is a 0. And similarly, when -2 comes, I can't help you with your sum, I am going to give you 0. So but when 4 comes, this guy is not going to help me, but I have a 4, and I'm going to help my next guy with a 4, okay? And now I have -1. So I am telling, so from 4 I add -1 to it and make it 3. So a prefix sum I am maintaining here. So this is my prefix sum. Then I find a -2. So here, can I make it better? So here my maximum sum at this point is still 4, but I can pass on. This guy can do something, can decrement this and make it 1, okay? And now comes the part. See here, this guy has a 1. So I am ready to give a 1. So here we can achieve something better than this, right? We can achieve a 2, and here the maximum sum so far is still 2, still 4, sorry. But here at this point, when 5 comes up, right? See, I am ready to contribute a 2 from all my previous occurrences, and if I include from all my previous occurrences, and if I don't include any of my previous occurrences, it is going to be 4. So here I am going to include all my previous occurrences. You remember from where we started here? It was till this point where we started 4, and then we included all of this. And then here when we came out here, we are going to say my maximum subarray sum till this point is 7, and from here on I can give 7 to the next guy. So here when -3 comes up, here -3, we are just going to take the maximum subarray sum to be 7 only till this point, but to the next guy we can give a helping hand of 7 minus 3, which is 4, okay? So so I would again like to break this down to you further. So if you observe this above array, this below array, okay, I will start with the below array because this is very crucial to understand. The above array is quite evident, it is so below array, we'll just go with the below array. So what the below array does is, it is just going to maintain the prefix sum, okay? So it is going to maintain the prefix sum. Initially it is 0, then we find -2, then since -2 is less than 0, we do not want to propagate it, because propagating this further would even decrease our sum. We don't want to help others with a negative value, we want to help them with a positive value. So here we again find it to be less than 0. Cumulative sum is going to be -5 here. So sum so far is going to be -2. It's going to be -2 plus -3. So this is going to be less than 0. So we are not going to pass that off. But here when it comes, here we have a positive value, and we want to propagate this positive value. So here we are going to make it. Here we are going to propagate 4, and now here again we are going to add -1 to it. And this time this becomes 3, and this time this becomes 1. Now imagine what would happen if a -1 was here. Let's take this example, okay? Imagine what would happen if -1 was here. Now if -1 was here, I would ask, is this rather than a -2, a -2 or a -3 would work better, because that would bring up my point here clearly. So let's take, if we had -3 here, Now adding 1 to minus 3, my prefix sum has to be minus 2, but I am not going to contribute a negative sum to my preceders. So I will make this 0 and I will update my maximum sum so far here to 4. You got my point, right? So that is what Kadane does. Kadane's algorithm says just keep summing the prefixes. Okay, so here just keep summing prefixes. Whenever you find something to be less than 0, right, that is the, don't pass it further, and let that guy take care of whatever has to be done. And that is how this is achieved. And then at every point we will when we get 4 here, we will try adding it to the previous one. Okay, I'll just code it out for you now. So let's go to this editor. So let me write an function here, public static void, or let's say an integer called algo, okay, which takes an integer array. Okay, so here, so what are we going to do? Let's say so here if you take the visualization part, so we had something called the maximum sum here, right? The maximum sum that we have encountered, so that variable I'm going to create. So integer max sum so far is going to be equal to integer dot min value, minus infinity, right? Minimum value. Then we need another variable to calculate the prefix sum, integer maximum sum ending so far, like, or I would rather call it prefix, is equal to 0, because here we didn't have anything. Now we would start a loop, okay, for int, or for int I is equal to 0, I is less than array dot length I double plus. Okay, now here I'll ask, see, we do not have to bother about anything. Okay, so now I would first take max prefix, okay, and I will add ARR of I. Okay, I'm not doing anything, I'm just adding it. And now if I find my max prefix to be better than my max so far, okay, I update my max so far to max prefix. Simple, right? Then if I find that my max prefix is less than 0, I don't want to propagate this, then I make my max prefix equal to 0, because I don't want to propagate that further, right? So then what is your answer going to be? Your answer is the max so far part. So this is your answer. Like if I just make a call sout call algo with array, right, you have to, like, the expected output is 7, and of course I forgot to tell you what the answer is. You start from here and go till here, right? So that is your this is the actually the part which gives you the maximum sum. So let me just run this to verify if this is correct or not. Oh, it's got an error here. What does this say? Okay, I'm not running some other program here, but that's fine. So just run Kadane's algo first. So it should give you, oh, it's giving me 10. Okay, that's, why is it giving me 10? It should give me 7, right? So let's just get into what's happening here and we'll debug this. So maximum prefix, we are adding it. If you find your maximum prefix, oh, here I have 3, so I think 3, this is the correct answer here, right? Till here it is 7, so till here it has to be 10, and here I made an example, it's minus 3 here, and if I make this minus, I hope it should work. Typo error, but it worked fine, right? So you get 7. So I hope you got my point here. Okay, so here maximum prefix is just, we are calculating the prefix of the subarray that we have seen so far. Okay, so nothing complex we are doing. So if my prefix becomes 0, then we don't want to propagate, right? Then we don't want to propagate. so we make it 0. Okay, and now if at any point if I find my if I find my prefix uh, to be better than the existing maximum, then I update my maximum. So if you see, the only part we are using this is for maximum update, right? Like an abstract sense, I'm telling you, you have a variable which is only used to keep track of the maximum. Say if I remove this line, this variable is only used for storing the maximum value. So if you find any value which is better than your maximum, you just update it, right? That is the only place which this is used for, right? So our entire algorithm lies in this thing, which is max prefix sum. This is initially 0, and so this is going to initially be 0. So whenever you start it, right? So whenever you start it, this keeps increasing. Like earlier it was minus infinity, so then it became minus 2. So it will be minus 2, it will be minus 2 because I cannot make it further, but now it increases to 4. So it increases to 4 in this iteration, so it remains 4, right? I hope you got my point here. Like, what are we trying to do with this? Sorry, let me just add up that line. So what is this used for? Maximum prefix sum is 0. So initially you won't have any prefix, this is 0, so this makes logical sense. You keep adding it to the cumulative array. So like you keep adding the prefixes, Now at any point you want your you find your sum to be less than 0, you update your prefix to 0, because you don't want that to be part of your maximum sum. I hope I'm conveying my point here. This is actually a very easy algorithm when compared to this n squared and n cubed algorithms, which are fairly more complex. This Kadane's algorithm is very neat algorithm, I would say, because it's pretty short to code up also, and the work it does is very amazing. Okay, so let me just summarize what I have just told you, and we'll just go to end up the video now. So here what is happening is we have a variable called prefix sum. So the only point of this is to keep track of the maximum value. Okay, that is clear, I believe. This is to keep track of the maximum value. So here okay, typo. Okay, anyhow, typos is not our issue now. This maximum prefix, what it does is, it whenever you find an element, you keep adding it. See, whenever you find it, whether positive, negative, whatever, just keep adding it. Okay, and now whenever this becomes less than 0, right? Whenever this prefix sum becomes less than 0, which means it becomes negative, we just want to ignore that part. We want to remove that, and we are going to make it 0. Okay, thereby removing it. And yeah, that is it for this video. If you have any doubts, I hope you will have a lot of them. Feel free to just ping me an example along with the doubt you have in the comment section, so that I could just trace you through the example you have and help you solve your doubt. So I would consider, please ping me the example of it, and also the example of it, and also the doubt you have. So both the example and doubt would make me understand your problem and also help you provide a better solution to your problem. Yeah, that's it for today's video. Thank you.